basically, I think most of the people who have joined have some engineering background, right? So you would have done your engineering in either computer science or electrical or electronics or maybe IT, whatever. So you would have come across different microcontrollers and microprocessors and even processors in your life. So my open question to you is, I mean, I don't need an answer, but I want you guys to think about this. So is it possible that a person can try to understand every processor out there in the industry? I mean, there are literally hundreds of processors, literally hundreds of controllers, starting from a very simple 8051 till maybe Qualcomm Snapdragon. So that's a very good processor, right? That runs our phones. So is it possible that a person can understand everything in between? Maybe, I'm an expert in all of the processors. I can code every processor. Do you think somebody can be like that? So the answer obviously is no. I mean, I cannot become an expert in every processor that's out there. But instead, what I can do is I can try to understand the basics, because every processor or controller or anything for that matter has a couple of well defined, well set out basics. So once you understand these things, it'll be very easy for you to understand any processor or any controller out there. It could be your MSP430, it could be Raspberry Pi, it could be any ARM based ARM Cortex. It could be anything for that matter. Once you get your hands on the basics, once you're very comfortable with the basics, you can go and attack any processor and you can start programming it right away. You don't have to worry much about spending time to understand it and going here and there asking people. That's not required once you get the basics right. So that's what I think. That's my biggest advice to you guys. So get your basics right and you'll be good to go. So one more good analogy that I can give is, most of you guys here know how to drive. You know how to drive a, say for example, Alto, Maruti Alto. So it doesn't mean that you cannot drive an Innova. Or do I have to go to a different driving school to learn how to drive Innova? Maybe a different one to how to drive Scorpio, or maybe should I do that? No, right? If I know what is driving, if I know the basics of what is a gear, what's an accelerometer, and blah blah blah, I can drive any car. So this is the same analogy can be applied here also. So once you understand what is a microprocessor, once you understand what is a microcontroller, once you understand the architecture, it's going to be same everywhere. Maybe 8051 is a very simple microcontroller, so you will have a very scaled down version of that architecture. And Qualcomm Snapdragon it's really good, so you probably have a scaled up version. So you'll have a lot more specifications, a lot more computing power, but the concept here remains the same. So that's the biggest key in this domain. So this is the contents for the quick webinar we're going to have. Motivation. So why would somebody want to learn the microcontroller and processor architecture? So why would you want to learn about it? So the answer is quite simple actually, because these are the pillars of the semiconductor industry. If I want to get into the semiconductor industry, like maybe Intel or Qualcomm, Samsung, Nvidia, AMD, Analog Devices, there's so many of them. These are very big companies, great places to work. And if you want to get into these companies, you have to understand the basics of what a microcontroller is and what a microprocessor is. And this is a huge industry. This got, as you can see, it was worth $481 billion in 2018. I think today it would be even more. It's a huge industry. It's very, very lucrative. It's a great job. It's there in almost every major city in India. So if you are from India, then I think you definitely have to look out for these industries. And apart from work, apart from job, in case you want to understand other computing units, like what is a GPU? I mean, I have a dream that I want to go and work on a GPU. I want to work on DSPs. I want to work on FPGAs, ASICs, SoCs. So the question is, where are you going to start? What are the skill sets that you need to go and work on them? Microcontrollers and processors are the definitive first thing that you have to learn. Because all these things, the GPUs, DSPs, FPGAs, they're all centered around a microprocessor and a controller. I take a processor core and then I go on adding different features to it. It ends up becoming a GPU, and based on the different features, it can become a DSP, it can become some other SoC. It's that way. But the central core is the microprocessor. So that's how, if you understand the architecture, you can really understand all other aspects. So I'll quickly tell you guys what a GPU is. So I think most of you would know, right? A GPU is a graphical processing unit. So this is the heart of all the audio visual effects that we see on a computer. You want to play a game and you're seeing a lot of good graphics. All such things are running on the GPU. And DSP is a digital signal processor. So in case I want to do some image processing or audio processing or video processing, I do that, right? I click a picture on my phone. I want to edit something. I want to add some brightness. I want to add contrast. Such things are done by the DSP. And what is an FPGA? FPGA is a very interesting thing. It's called a field programmable gate array. Say, for example, you're a designer, you've got some ideas, and you want to make an IC. You say that, okay, I want to make a chip that will detect a person. When a person comes closer to the chip has to sound an alarm. So how would you do that in the first place? So you're going to first come up with a layout, you're going to come up with the schematics, and you actually burn it on an FPGA. So FPGA is something wherein I can create my own chips multiple times. So it's very similar to a microcontroller. As a microcontroller can have different functionalities, right? So I can write a microcontroller to maybe play some sound, play some music. Similarly, FPGAs can be used to create a microcontroller itself. So today I want to create a microcontroller of this specification. I can do it on my FPGA. And the same FPGA can be used again to create a totally different microcontroller. So that way you have just one board and you are creating so many new designs. And with that, you can do a lot of testing and simulation and try to understand if your designs are good or not. So that's how FPGAs are used. ASICs is application-specific ICs. So I've got an application, say, for example, satellite communication. So I don't want to use an Intel i7 processor for that. So I want to have my own processor for it. So that's an application-specific IC. So an IC that's meant for a particular application. And SoCs are something that are really, they're the buzzword today. In fact, if you go to the industry today, everybody's talking about SoCs. So SoC is a system on chip. So this is a huge chip that contains your processor, it contains different camera modules, it contains a GPU, an on-chip RAM, and so on. So Qualcomm Snapdragon is an SoC actually. So in case you want to understand any of these things, your starting point is going to be understanding the architecture of the microprocessor and a controller. One of the other reasons for you to study this would be to, this opens infinite number, it opens doors to infinite number of applications in the industry. I want to work on IoT. So you definitely have to use a controller for that. I want to work on automotive electronics. That also uses a controller. I want to work on 5G. I want to work on 4G, 5G communication. That also has the same controllers and processors in it. So, I mean, you can think of it, right? You can think of literally infinite ways in which it can be used. In fact, ARM, which is a very famous provider of the license for processors, sells over 1 billion devices every year. So 1 billion devices sold just from a single company every year. So you can understand how lucrative this is. One of the applications would be IoT, automobiles, mobile communicating devices, televisions, medical electronics, drones, aircrafts. I mean, you name it. Controllers and processors are there everywhere today. So we are pretty much surrounded by these devices. In fact, I'll give you a very nice example. So I've connected a small USB hub to my computer now. In fact, a lot of people might not know a USB hub will have a controller inside it. So, USB hub looks very simple, right? That, okay, it's just a simple connector, but even that has got a controller in it. So that's how important it is. So moving on. So I'll probably give you a small introduction as to where all this started. So this was somewhere in 1944, the World War II was on and everybody was wanting to have their own intelligence unit. And that's how the first computer came into effect. So it seems they wanted to do a lot of cryptography and, they wanted to understand what the other person is saying. So that's how they made a computer. So that was the ENIAC computer in 1944. This actually used something known as vacuum tubes. So there was no transistors back then. So they had to use all these big bulbs, and a very simple computer, maybe whose computation power is equal to a calculator in today's terms, occupied an entire floor of a building. Just imagine in those days, a calculator sized computer. I mean, something as simple as a calculator required a building sized of hardware. So those were the very tough times in which a computer was born. Somewhere in the 1950s, the transistor was invented. So this was something of a revolution, as in People had to use huge vacuum tubes that required thousands of watts of energy. And here is a transistor that can do the same job in probably microamps of energy, in microamps of current. So that was a revolution which started off the invention of IC and then so on, memory units came. And that's how 1970s and 80s was very exciting time for the computing systems. So people started coming up with different chips. So there were companies like IBM, Intel, and Texas Instruments that these guys came up with chips that could do a lot of things. And somewhere in the 1990s, Intel came with the Pentium. So I'm not sure if you guys were born that time. I don't know what is the age of the students that have joined today. But Pentium was a pretty cool processor, as in it had two cores. So core is a computing unit, right? I think most of you would know. Today's Intel i7 will have probably 8, 16 cores. I don't know. The number keeps on increasing. But Pentium was the first processor to have two cores, that is dual core. So before that, everything was done by a single core. So there was a bottleneck. I mean, people could not get any faster. So Intel guys thought, okay, now let me put two cores in my CPU. Let's see what will happen. And that's how Pentium came into being. And so we are somewhere here. If you can see my cursor, I'm moving it on SMP and HPC. So today's computers are either SMP, that's symmetric multiprocessing, or HPC. HPC is high performance computing. So you have in SMP, you've got multiple cores of the same type. Say, for example, I've got an octa-core processor, right? So that means there are 8 different cores, the same type of cores. They're going to have the same specification, same memory requirement, and everything. 8 of them will be doing the job of a single one now in an octa-core machine. So that is what is an SMP. And high performance computing is basically yesterday's supercomputer. You would have probably read about how supercomputers were, designed. It had thousands of smaller computers running together and things like that, right? So that's what is a high performance computing unit. It's basically you cluster in different computers together and use it for a single application. So we are in this era now. So we are in the SMP and HPC era now. What are the current trends? So what does today's microprocessor and microcontroller look like? So most of them are either a RISC or CISC architecture. So this is a very important term that you will see in the industry, as in ARM architectures are all RISC-based. So the chips that are running my phone, the chips that are running my tablets, the microcontrollers inside my IoT device, all of these are RISC-based. And the chips that are running on the server, on a supercomputer, on my desktop computer, so these are all CISC-based. So I have an open question for you. I mean, you don't have to type in the answer, but I have a question on which I want you to think. What do you think are the characteristics of RISC and CISC? So I gave you 2 examples, right? Maybe I can give you a minute to think about this. What do you think makes RISC good for mobile phones, tablets, IoT devices, handheld devices, etc.? What do you think CISC makes it good for servers, supercomputers, desktop computers, etc.? I wish that somebody will have already guessed it. So RISC is good for low power applications. So I mean, I don't want to have a phone that I need to charge every half an hour, right? And CISC is good for high power applications. So I need a server that has to be on the top of the speed at every point in time. I cannot expect I log into Facebook and it's like, oh damn, nothing is loading. That cannot happen. So CISC is good for high power applications, high performance. RISC is good for low power applications. So RISC stands for reduced instruction set architecture, and CISC stands for complex instruction set architecture. So these are very 2 important terms in the domain. So I think there's something that you should definitely note deeper. And the next point in the current trend is how big is the microcontroller? So is it a 6-bit architecture, or is it is it a 8-bit architecture, or is it a 64-bit architecture? So as some of you would have read in your colleges, that 8051 is a 8-bit microcontroller, right? Does anybody know about any 6-bit, 64-bit microcontroller or a 64-bit processor? Intel's i7 and Snapdragon and Exynos from Samsung. So all of these are 64-bit processors. So this basically tells how big your resistors are. So resistors are the most basic fundamental blocks of memory in a chip. So this will basically tell you how big this is. So each resistor in an 8-bit architecture will be 8-bit wide, and it will be 64-bit wide in a 64-bit architecture. And then today's processors abide by a bunch of rules called instruction set architecture. So if you want to be an expert in the domain, in this particular domain, you will have to understand what the instruction set architecture is. So instruction set architecture, or ISA, is basically the contract between the programmer and the hardware. I mean, I'm a programmer. I need to know what the hardware is expected of. So is it an 8-bit architecture, or is it a 64-bit architecture? What are the different kinds of memory that this hardware supports? Does it have a cache? Does it have a RAM? How much RAM does it have? And does it have a flash? How big the flash is? Such things. Instruction set architecture also talks about the different architectures. Like, does it have a branch predictor? Does it have a speculative programming? Is it a super scalar architecture, or is it a VLIW architecture? Does this support multi-threading? So multi-threading is wherein I can run two or more simultaneous threads. I mean, I can run two or more threads simultaneously. And does this support parallelism? That is, can I do two tasks at the same time? Can I play music at the same time? And can I also edit some documents at the same time? So does my hardware support all this? So these questions are actually answered by the instruction set architecture. So if you take any course and if you want to understand the domain, then you have to spend a lot of time trying to understand what the instruction set architecture is. So once you know this, you can apply it to any processor. Okay, so you'll think that, okay, this processor now has only 12 MB of cache. The other one the other one that I use had 18 MB of cache, and processor B has just 2 GB of RAM. Processor A has 16 GB of RAM. So all these specifications are part of the instruction set architecture. And something that's dedicated to microcontrollers. So what are the different features a controller has? So does it have an ADC? Does it have a DAC? What are the different communication protocols like SPI, CAN, I2C, UART? So what all does this support? Does it support Bluetooth? Does it allow Wi-Fi? And how many pins do I have? How many number of peripherals do I have? Can I use this for something else? So these are the information that you have to gather about a microcontroller. So I've got two interesting images here. So the one that I am showing right now, the purple one. So this is a picture of a core. So this is the entire SoC. You have 4 cores in it. So this will be quad core SoC, and you have got a shared cache, and you'll also have dedicated caches. You've got a PCIe, which is the interconnect between each core. So this is the I'm not sure which processor this is, but this is how most of the today's processors look like. And I put in a picture of an Arduino. So Arduino is a very simple microcontroller that's really popular. So if you want to really start working on Arduino, you don't have to know anything, right? I mean, I know a lot of people who have no background in engineering, but they've come up with great applications using Arduino and Raspberry Pi. I mean, that's absolutely great, but we as professionals have to understand more than that. So we cannot restrict ourselves to Arduino or Raspberry Pi. We have to even build great codes with just a simple microcontroller, anything that's available to me. So that should be your aim while understanding this domain. So here I say microprocessor and controller, the future. So going down the line, how does it look 10 years from today? What would the future look like for these devices? So as I previously mentioned, system on chips are the new thing. So I put an image here. So this is an SoC. So this SoC contains a controller unit in the center, and there are so many different other modules. So you've got an ADC, you've got a cap sense, you've got amplifiers, you've got UART, you've got PWM, you've got GPU, you've got DACs. All of them are on the same chip. So you don't really have to bring in additional components from outside and have the headache of connecting them. And you're worrying, oh my God, the UART module is not working, the Bluetooth, the baud rate is not correct. What do I do? You don't have to worry about them in the future. I mean, you'll have chips that have everything inbuilt in it. You just have to take it and use it for your application.